Alright guys, so here we want to talk about the Monty Hall problem, but we want to functionalize it, we want to simulate it in Python here on Google Colab just to make more sense out of it, just to play this game multiple times. And once we functionalize it, we could call that function hundreds of times just to see what is the winning likelihood of a particular choice that we make. Now, just a reminder of what this Monty Hall problem was. There is a video earlier, but I will just review it one moment. We actually did calculate the probabilities for it in a different video, but today we're not calculating probabilities. We're playing this game on Python. Remember what the Monty Hall problem really was. You have to make a pick, and behind one of the doors is a car. If you choose the right pick, you win that car, but if you choose the wrong door, you end up with a goat. So that is the premise. But once you make your initial pick, say you chose door 1, the host then opens one of the other goat doors and then gives you a second choice to make. Do you want to stick with your original decision, or do you want to switch to the other unopened door? So if you chose door 1, the host would open door 2 to reveal a goat, and then the choice is yours to make. Do you want to stay with your original first door, or do you want to switch to the unopened third door? This is what we want to implement in today's Python code. Now, the key thing to remember here is that we want to implement these choices in Python in terms of coding. And the two question marks that are really there to basically code are: how do we know how do we code the mechanism where we exhaust the possibilities of the doors to be chosen, right? So that is exactly the trickier part in this when we come down to simulation. So we're going to go over this step by step and simulate this entire problem in the Python code, right? So I have the Python code with me. This is the function definition in its entirety, and we will do justice to it by going over each line step by step to make sense out of what it's doing. Now, right away, when we look at a function, we want to understand what does it really do and how does it work. So we notice that this is the function name. What we see here is an input to the function, and this right here tells us that this is the start of a function. It's actually a function definition, right? So that is the syntax that we work with, and everything then from this indentation onwards, from line 2 onwards, is the definition of the function all the way to line 33. So that is what it is. Okay, now the first thing that we have to get done is set up these doors, right? And since there are 3 doors, we could essentially define an array where we say an array could have 3 possible values, and these 3 values could be filled with 0 or 1, with 0 referring to a goat and 1 referring to a car. And we could initialize our array in this manner where we say, okay, we're going to set up the car in door 3. Okay, so you don't know that, but we have to start with something. Then what we do is we call the random library, and we call the shuffle mechanism, shuffle function from this library, and we shuffle this array, these doors. What that really does is it then shuffles the value of 1 between any of these 3. So now we don't know where the car is. Okay, that makes it fair. But we could always print the doors. We could print this array to see where the 1 is, where is the car, right? So this is one thing we would do just to keep track of things. But for now, since we are trying to make sense, let's just say after shuffling, the car was in, let's just say in the central door, in the door in the middle. Okay, so that's something we could assume at this point in time. Obviously, when we run this code, we are going to print this, and we will see this printed where the car really is. Now, the next stage in here is then for the contestant to make a decision, right? This is the first choice, the first decision that they make, which is which door are they going to choose, right? And we could randomize this choice because it has to be a door between 0 and 2. Python, the start of the number is from 0 1 2. That's the 0 is the first index value. So we say let's choose an integer between 0 and 2, meaning 0 1 or 2, and we make that guess random. Okay, so we randomly choose the first door, and we store that value, which would be 0 1 or 2, in the chosen door variable. Okay, so let us just for the sake of this simulation, let's just say we chose the third door, meaning we put up a value of 2 in this specific variable. Okay, so we chose this right here, right? So 2 would correspond to this particular door. 0 1 2, that's the syntax in Python in terms of index. Okay, so we're just going to write it here for simplicity. Okay, so we've set up our car in one of the three doors. We've chosen the first pick, and that's fine. What happens next is the host then reveals a goat door, and that's the next stage in this. The host has to reveal a goat door, but then we have to understand the choices that the host has. He cannot reveal the door that you chose. He cannot reveal this door. The game would end. He cannot reveal the car door. The game would end there and then, right? He has to give you a choice to make. He has to confuse you. So he only has one option to open at this point. He only has the first door to open. But when we're trying to write this in terms of code, we have to exhaust all possibilities, right? It's possible the car was another door. It's possible you chose another door. Remember, we randomized them. So we've got to exhaust all possibilities. And one of the ways to do that is to set up a for loop, meaning we would check for each of the three doors whether each of these three doors are our chosen doors or they have a goat in them. So these are the two checks that we are going to make. Now notice the checks that we are making here. This is the first check. Now, not exclamation and equals to, this here means not equal to. If I is not equal to the chosen door, we have the chosen door with a value of 2, right? And the other check that we are making simultaneously at the same time is this check. Doors I is equal to 0. Okay, so this is checking if it has a goat. So this is a goat check, whether this has a goat, and this is checking if it's a chosen door, right? If it's our choice. So if both of these, right? So it's basically checking these two things simultaneously. If I is not, I here is referring to a door. So we are running a for loop, which means we are iteratively running this code, these block of lines 4, 5, 6, and 7. We are iteratively running them. If for three different values, which are I equals 0, we run these 4 lines, then we increment the value of I to 1, we run these 4 lines, then we increment the value of I to 2, then we run these 4 lines. There they are. So we run these 4 lines for I0, I1, and I2, one by one, until we have met this condition if, and the if condition will break the loop, right? So let's run this once for clarity. Okay, so for the first case, for the very first time this for loop is going to run, we're going to have I equals 0, and that's okay. Now we run these four lines, right? So I is 0. If is 0 not equal to the chosen door, the chosen door is 2, so 0 is not equal to 2. That makes it a correct comparison, right? So this makes it true. 0 is really not equal to 2, and that's fine. So we have our first check in success. Chosen door was 2, 0 is like the first door. Yes, the first door that we are checking is not the chosen door. That's fine, that's the first check. The second check is whether or not this has a goat. So we index the doors, right, with the I. Remember, I is 0. So this is checking whether the first door is in fact having a 0 or a goat in it. And yes, it does. So this check is also in success. So you've got both these checks in success. The chosen door, the first 0I is in fact not the chosen door. Yes, that is a successful check. And the first door has a goat in it. This is also a successful check. So both these checks are successful, which means the if statement has in fact gone to be true, and line 15 and 16 will get executed. If one of these checks were not true, these 15 and 16, 17 lines will not get executed, and then we would have gone on to I equals 1, right? We started to I0. So this check, since these checks got completed, we head on to line 15, and that means we can reveal this ith door, which is the 0th door, right? So this 0th door can be revealed, and we call it the reveal door. That's the value we store in this. We store 0 in this, and we also print it for good measure, right? And then importantly, we break the loop. So this break command is actually going to break the for loop, which means we have revealed the door. We don't need to check for the other two doors, right? Remember, this block of code, 12 to 17 lines, was to reveal a goat in one of the doors and then move on and ask the contestant to stick or switch with their original decision. So we insert a break command here to break the for loop. If these conditions had not met, we would have gone on to check for the second door, right? But in this case, these do meet, so we break this for loop. We don't need to check for the rest of the doors. Just to summarize this part, 0, the first door, was not our chosen door. We had chosen door 2. We had chosen this last door. This was not a chosen door. 0th door was not a chosen door, which made this check a success check. Then the 0th door was in fact, yes, it was a goat door, which also makes this a success. So both successful conditions for the if checks. That means line 15 and 16 do get executed. That's the nature of if statement. They do get executed, and then we break the for loop. We don't need to check for I1 and I2. So now we've got our reveal door. Here we are in the game. We chose door 2. The host revealed door 0. And now we have a decision to make to whether to stick with this door or switch to this central door, right? So how do we implement this? Now this is an important part because it now uses the input that we fed, right, to this function, this input switch. So we always feed for this implementation that yes, we will always switch. Whatever our original choice was, we're always going to make a switch from that original choice that we made. And what that means is, since we chose door 2, we are going to switch now to the other unopened door, which was the central door, right? The door 1 is out of the, this door is out of the equation anymore because this has already been revealed. So we switch from this door to the central door. And what that means is, what is the value stored in switch? If this condition meets, only then we execute this code. And we said we're going to always feed yes to switch. This is how we're going to call this function. We're going to feed a yes input to this function, and here we are checking whether or not we have a yes input in this variable switch. And if we do, which we do, we're going to execute this block of code, right? Line 21 to 25. Again, we have to generalize this, so we check the possibilities that are there, and we can write them out for clarity. Okay, so let's write these out from line 21 to 25. Again, we have a for loop, which means, and for I in range 3 essentially means that we are again checking in line 21. We are going to iteratively see first, set up the value of I as 0, execute the code, and then I1, execute the code, and then I2, and then execute the code. So this is again something that we're going to do iteratively. So for the very first time, I is going to be 0. Now let's execute these lines for I equals 0 first. Okay, so what are we really checking in this if statement, line 22? We're checking if I, or 0, is not equal to the chosen door, and I is not the revealed door. Okay, so you have switched, but you are checking if it's not. Remember, in our array we still have all three doors. Yes, in the game door one, this first door is out of the equation anymore, but for generalization we still have to go through these three checks in code, right? We still have to check for all three doors. So this is handling that part. If I is not the chosen door, if I is not the chosen door, which was um, this specific door 2, right, with index 2, if it is not the chosen door, and 0 I is not the revealed door. The revealed door, remember, had 0 stored in it. So let's just write these two values down. For this first case, we have I0. 0 is not equal to the chosen door. The value of the chosen door, if we remember correctly here, is 2. Right? So if 0 is not equal to 2, which it really is not, which means this specific check results in a success, and if 0 is not equal to the revealed door, which is in fact 0, right? So now in this case we see that this is not true. 0 is not equal to 0 is not true. These are equal. These are equal in fact. So this check fails. So what that means is we cannot update our value of the chosen door, right? Remember, the value of the chosen door needs to be updated. So this check fails. It does not allow us to update the value of the chosen door. The problem here is, and why do we even have this check in place, is because when we set I equals 0, we are basically using this value to be used for the new update or the new chosen door. We cannot set chosen door to 0. This door was out of the equation. We cannot set our new updated door to this value, right? So it makes sense that we have this check failed, which means since this check does not this check gets failed, we move on to the second value of I, right, which is now I equals 1. So this check in fact failed. We now head to I equals 1 right here. So when we head to I equals 1, which means 1 is not, and I will erase this and put these checks again for good measure. 1 is not equal to the chosen door. Remember, the chosen door was 2, and yes, 1 is really not equal to 2, and that results in a success for our check. And let us just see what happens here. Now I is 1, and we say 1 is not equal to the revealed door. Revealed door was 0, right? And this is in fact true. Notice that this check says that 1 is not equal to 0, which really isn't. 1 is not equal to 0. So this results in a successful check. Now, what this does is it puts chosen door's value 1 I as 1. Remember, the current value of I is 1, so this makes chosen door's value updated to 1. Okay, so and then we print this and then we break the loop, because now we don't need to check for the third I. We have updated our value for the door from 2 to 1. This is what we managed to do, right? So in summary, for this block, for this code block, what this code block really does is it updates the chosen door for the contestant. How does it do it? It makes two key checks simultaneously in line 22, and it iterates over the doors. the two checks ensure that the door in question is not the originally chosen door, and it also checks if it's the door in question is not a reveal door, right? So essentially it is eliminating your original choice and the reveal door, and it comes to the conclusion that the only left, the remaining door becomes your choice. That is what it assigns to I, or the chosen door variable, right? And we have this set up. The final part of this implementation now checks out whether or not the chosen door, the updated value of the door, whether or not it is equal to 1, whether or not it has a car. So your updated value of the chosen door is 1, right? In line 23 we had this updated as 1, and since it is 1, we will check it against our against the array that had the car value set up in it, and that array was originally defined as 0 1 0, right? This is what we assumed, and we do end up with this. Our chosen door's updated value is 1. That is where the car really is, and this should result in a print 1, right, for us, WN1. So that is, and we're going to return the value of true if we have won from this function. So that is the logic behind this implementation. Let's actually go ahead and run this code and play this a couple of times just to make sure that we arrive at the same conclusion. We're going to run this function definition, and we're going to play this game once. We feed in the true value to it, and let us just see what it does. Okay. So we since we said that this is our input switch, right? So we're looking for the input switch, and this input actually has to be equal to yes. Unless this is equal to yes, we're not going to be able to go into this if statement, right? So this is how, and we're going to play. We can run this cell multiple times to see how the results show up and how they go on about, and that's fine. But let's just read through these comments once. So for in this particular case, we had these doors set up in this way where we had 0 0 and 1. Remember, these are the print statements that we have had here. We have printed our doors after shuffling. The car is in this last third door. We chose door 2, which is 0 1 and 2, and the door that was revealed was door 0. And since this was our original choice, we made the correct choice initially, and we reveal, and after the door was revealed, we had a choice to make to whether stick with the original choice or switch to the other door. And we chose to switch the door. We always choose to switch the door. This is why we fed in yes. So we had this choice, but we switched to the central door, and as a result we lost, and the false was returned by the function. Okay, so in this particular instance we lost this game, and that's okay. What I have next is an implementation where I have commented out these print statements. If I play this game 100 times, I don't want this to be printed 100 times. I only care about the outcome, right? So I'm going to save these outcomes, and I'm going to play this 100 times just to play it large number of times to see what really happens for most of the times if I play this many times. So I'm going to simulate this 100 times. Call wins switch as 0, wins no switch as 0. These are the initializations. I'm going to play this 100 times for I in range 100 here, because I'm going to play this 100 times. And remember, we're going to iteratively, this is what the for loop does. It executes line 6 and 7 100 times, and the Monty Hall function gets an input yes, and we see if the output from this function is in fact true. Then true equals true will result in a success for this if statement, which will execute line 7. So if we get a true output from this function, this line 7 gets executed, which is simply adding 1 to the wins switch counter. It starts from 0. So after 100 times, when this code has run 100 times, we will see how many times did this counter get incremented, and we can always find a percentage. The number of times it gets incremented divided by the playing times, which are 100, we multiply it with 100 to find the percentage. So if we play this 100 times, it seems to be printing something. Monty Hall switch. Okay, we seem to have a print command set up, which we don't want. There is probably a print command that is still showing up. Let's see. So we have this function definition. Oh, maybe we did not run this cell because both the cells have the same function name. Maybe we probably had this implementation run, but let's just recheck once. Okay, we have this cell run. So this is our latest implementation. And then let's run this. Yeah, okay. So it says that for 100 times, 62% of the times we're going to win if we switch. Remember, that's the hypothesis. We switch each of these times and we see whether we win or not. Turns out that this is somewhat a number in the 60s, okay, which is a high probability of winning. It's more than 50, right? Which is an interesting note to make. But let's just increase the number of times we play this and see if we can approach a particular value. Actually, we're trying to hit a value of 67% or 66.7%, the 2 by 3 probability that we came across in one of the other videos. And if let's add another 0 and play this 10,000 times, right? So we kind of approach the 67 percentage number if you play this large enough time, and that is because if you play a game large number of times, you end up with a probability, you end up approaching the exact probability that you would calculate analytically or mathematically. So that is the implementation of Monty Hall in Python, and you could play this hundred thousand times to arrive at the same conclusion that we did analytically in one of the other videos.